Imagine a world where multiple scientists claim to have discovered a new element, each giving it a different name. Confusing, right? Well, that's exactly what happened when both American and Soviet scientists discovered element number 104. One called it Rutherfordium, the other called it Kurchatovium. So, how do we resolve such naming conflicts in chemistry? That's where the International Union of Pure and Applied Chemistry, IUPAC, steps in. As more and more super-heavy elements beyond uranium, called transuranium elements, were synthesized, there arose a need for a universal naming system. These elements are extremely unstable and produced in trace amounts, often just a few atoms, in high-energy particle accelerators. With such a global scientific race to discover them, IUPAC created a temporary and systematic nomenclature. It ensures every new element has a unique identity based on its atomic number, no matter where or how it was discovered. This was chemistry's way of bringing order to the chaos. So how does IUPAC systematically name these elements with atomic numbers greater than 100? It all begins with the digits of the atomic number. Each digit from 0 to 9 is assigned a specific root derived from Latin or Greek. For example, 0 becomes nil, 1 becomes un, 2 becomes bi, 3 becomes tri, 4 becomes quad, 5 becomes pent, 6 becomes hex, 7 becomes sept, 8 becomes october, and 9 becomes in. These roots are then joined in the order of the atomic number, and the suffix IUM is added at the end to form the name. For instance, element 115 is named Ununpenchim, built from Un for 1, another Un for 1, and Pent for 5. The symbol for this element is UUP, made from the first letters of the roots. This systematic approach allows us to name elements as soon as they are created, even before they receive a formal name. It's like giving a newborn baby a temporary tag until a proper name is chosen. Let's walk through a few examples to make this naming system come alive. Take element number 104. Its digits are 1, 0, and 4, so we take the roots un, nil, and quad, combine them and add IUM to form the name Unalquidium. Its symbol becomes UNQ. Similarly, for element number 107, the digits are 1, 0, and 7. That gives us the roots un, nil, and sept, forming Unalseptium with the symbol uns. And for element number 110, the digits 1, 1, 0 give us Unanilium with symbol un. One important point to note, when combining these roots, we avoid repetition of similar letters unless needed. This helps maintain readability and pronunciation. On the screen now, you'll see table 3.5 from your insert. Textbook, it shows the IUPAC names and symbols for elements from 101 to 118. These temporary names act as placeholders until official names are granted. But when do these elements get their final names? Once a discovery is officially verified through repeated experiments and international confirmation, the discoverers are invited to propose a permanent name. These names usually pay tribute to notable scientists, countries, cities, or laboratories. For example, element 106 is named Seaborgium after Glan Seaborg, who contributed significantly to the discovery of transuranium elements. The final name and symbol must be approved by IUPAC through a global vote. Let's take another example. Element 113 was originally called Ununtrium with symbol UUT. Later, it was officially named Nihonium, symbol NH, to honor Japan, where it was discovered. The process reflects global collaboration in science and gives lasting credit to contributions in nuclear chemistry. You might see a flowchart on your screen now showing the journey from atomic number to temporary name, then to final recognition and formal naming. In recent years, many newly discovered super-heavy elements have been formally named, and their names reflect the diverse origins of discovery. For instance, element number 114 is now called flerovium with the symbol Fl, named after the Flerov laboratory in Russia. Element number 115 is called moscovium, Mc, named after the Moscow region. Tennessine, with symbol Ts, represents Tennessee in the United States, a center for nuclear research. And the heaviest of them all, element 118, is called oganesson, symbol Og, named after the renowned physicist Yuri Oganesson. Each of these names is more than a label, it's a tribute, a legacy etched into the periodic table. As you view the modern periodic table on screen, notice how the last row now glows with these international achievements. Now let's apply what we've learned. Suppose scientists synthesize a new element with atomic number 120. What would its systematic name and symbol be? Let's decode it using our digit roots. 1 becomes un, 2 becomes bi, and 0 becomes nil. So when we combine them, we get un, bi, nil, and then add the suffix ium. That gives us unbinilium, spelled unbinilium. The symbol would be UBN, U for un, B for bi, and N for nil. Even though this element hasn't yet been discovered, its name is already predictable thanks to the systematic rules by UPAC. This prenaming strategy helps chemists around the world refer to undiscovered elements consistently in research and discussions. So let's take a moment to review what we've uncovered about naming elements with atomic numbers greater than 100. These elements are often synthetic, unstable, and discovered under competitive research conditions. To maintain neutrality, UPAC provides a temporary systematic naming method using Latin and Greek roots for each digit of the atomic number. The name ends with IUM and the symbol is a 3-letter abbreviation derived from those roots. Once a discovery is confirmed, the element receives a permanent name that often honors a place or scientist. For example, Anantrium became Nihonium and Ananpentium became Moscovium. This ensures chemical naming remains fair, international, and informative. I hope this session helped you appreciate how chemistry isn't just about reactions, it's also about rules, recognition, and respect in the scientific world. See you in the next topic, where we continue our journey through the elements of the periodic table.